Hi, this is Mrs. Kidman, and in this video, we are going to be discussing another way to apply quadratics. Now, this time, we're going to be doing something using optimization. So what does optimization mean? Well, according to dictionary.com, optimization is making the best or most effective use of a situation or resource. So really what that means is when we have this mathematical concept, optimization means I want to find the maximum. So some of the questions where we use optimization are when we're looking at something like, how can I make the most money? How much money should I charge for this school play so that we bring in the most revenue? Or how much, what should my area be? How much length and width, what are my dimensions of a enclosed structure that I'm building? Should I use based on a certain number of supplies? I'm trying to make the most effective use of my resource or my situation. So if I'm going to run a school play, how much money should I charge so I can make the most? If I'm trying to build a fence and I'm limited on my resources, what should my dimensions be so that my 500 feet of fencing builds the biggest enclosure? That's kind of what we're looking at when we're talking about optimization. So in this video, we are going to talk about mostly this first one here, or the second one here. What do I need to do to have the biggest area for the least amount of supplies? So that is kind of what we're going to look at in this first video. Please check out the next video because in the next ones, we're going to discuss what we need to do to make the most money, or is it even possible to afford something? Because this is so important as you're running fundraisers, as you're putting on activities and events. We want to figure out, can we even bring in as much money as we want to doing this activity? Or can we do something like that? So let's take a look just at these area questions first to optimize how much space we have. So in this first example here, you have 500 feet of a fence to use to construct an enclosure for your pet velociraptors. That's right. Welcome to 2020. We have velociraptors. So we have pet velociraptors. We're trying to build an enclosure for it. We have 500 feet of fencing to use to build that enclosure. What we want to do is we want to give them the most area possible. So that most area is where the optimization comes in. And what we need to do is figure out what should the dimensions be so they have the most space. So let's first take a look at our area here. So we're looking at area, and remember, area is length times width. And that's great. Super important. Here's our length, here's our width. The area inside is going to be length times width. Great. But that doesn't include that 500 feet of fencing aspect here. That fencing is what's going to be around the outside. Now remember the outside of a rectangle. If we're adding up those pieces, we call that the perimeter. So we've got the perimeter as well. So let's write an equation for an area and a perimeter and use those two equations to figure out how we can optimize that length and width so we get the biggest area with our restricted perimeter. So our perimeter here, or the amount of fencing that we have, is 500. And that 500 should be a length plus a width plus a length plus a width. So I have two lengths and two widths. So that 500 feet of fencing needs to equal our two widths plus our two lengths. And we need to figure out what those are. So notice how over here, I've got a width and a length. And in my area equation, I also have a width and a length. Both of these things are written in terms of two variables. And it's difficult to solve for a variable if it's written in terms of two variables. So what I want to do is I want to take my perimeter example here, and I'm going to rewrite my perimeter equation so that it is equal to one variable. We have done this in math before when we are solving equations, and that's kind of what we're going to do here. We're going to solve our perimeter equation for L or for W, we can choose, substitute that value into our area to get a quadratic to represent our area. And that quadratic will show us the relationship between the area and either the length or width of our shape. And then we can use that to figure out what is the maximum area that we can get based on that length or width. So let's take a look here. Let's solve for width. So the way we're going to solve for width is I'm going to subtract my 2W from both sides, or my 2L. Well, we're solving for width. Subtract the 2L on either side. So I'm trying to get this W all alone. And I get 500 minus 2 times the length equals 2 times the width. But I want just the width, so I'm going to divide everything by 2. And this shows me that my width is going to be 250 minus my length. And that makes sense because our width is going to be half as much, our width is going to be half. Yeah, that makes sense. It's going to be half of what we have, divided all by 2. So now I'm going to find my optimized area, I'm going to write my area in terms of width. So instead of writing length here, I'm going to substitute in my width equation. So I've got 250 minus the length times the length again. So instead of writing out width, we replaced it with our equation for width. So then we want to solve this. So our area equals, well, we're going to multiply this in to get a quadratic. 250 times the length minus the length squared. Fantastic. Okay, I'm going to write this in standard form just so that we're aware. So negative length squared plus 250 times the length. So that is our quadratic there. So what I'm going to do is I'm actually going to graph this in Desmos and show you what this looks like. So as we graph this in Desmos, we have our area equals negative length squared plus 250 times our length. And this is what it looks like here. Boom. Look at that beautiful quadratic. So let's see if we can stretch it out here. So we're going to go up. Look at how high it goes. It goes up and up and up. And here we go. So this quadratic here that we're looking at is showing us a representation of something very specific. It shows us that here at the highest point, we have the relationship between the area on one side. So this side that's going up, our y-axis is our area, and our x-axis is the length. So as our length increases, our area goes up until it hits a certain point, and then it comes back down. And we want to figure out what is this point at the top, because that is when our area is going to be at its highest, or what is the maximum of this. Now, we can use Desmos or a graphing tool, like our graphing calculator, to calculate this, or we can use the equation to find the vertex based on standard form that we've used, and that's how we're going to do it here. So to find that peak point, or that highest point as we see in our graph here, I want to find the vertex of our polynomial. So let's find that vertex. So to find the vertex, remember our x value, or our length in this case. So to maximize our area, our length is going to be the peak of that thing. So it's going to be our negative b value, which is negative 250 over 2 times our a value, which is negative 1. And as we simplify that, I get negative 250 over negative 2, and that becomes 125 feet. So what that tells me is that in order to get the max area, my length needs to equal 125 feet. Perfect. So my length is 125 feet. So if our length is 125 feet, what does our width need to be? Well, we can figure that out just using our perimeter equation. So I've got 500, and we have it right here. We can use this, or we can use this right here, which tells us what width is. So width equals 250 minus our length, which is 125. And that means that our width is also going to be 125 feet. So when we're talking about our dimensions here, our length is going to be 125 feet, and our width is going to be 125 feet. Now let's double check our graph to see if it agrees. So when we are at our peak point here, our length here is at 125. And total our area is going to be this 15,625. Now, hopefully 15,625 square feet is going to be enough for our velociraptor. If not, we're going to have to figure it out. But this is the dimensions that we need to get the largest possible area, because that area, remember, area is feet squared, and that square means that it's going to be represented by a quadratic. And so we can use that quadratic and find the maximum of it to optimize how much space we need. So that is our first example here. Now, I want you to, we're going to look at this next one all together. We're going to go through this one a little bit faster. So you have 600 feet of fence, and we want to construct an enclosure for your goats. No longer velociraptors, now we have goats. You want to have 2 enclosures, but they can share one side as modeled in our picture. So what lengths should they be? What are the dimensions of our large rectangle? So let's take a look. I'm going to call this the length, and I'm going to call this the width. Now, area is going to be length times width, but our perimeter, in this case, how much our fencing is. So we've got 600 feet of fencing, right? That needs to cover 2 lengths, plus it needs to cover this width, plus this one, plus this one. Notice those are all the same. So our 600 feet of fencing needs to cover the length of 2 lengths, or the amount of 2 lengths and 3 widths to get that 600. So what we want to do is, just like in that last problem, I want to solve for either the length or the width here, substitute it into my area equation, and then use that quadratic that our area shows to calculate what is the most optimal area that we can use. So I'm going to solve for length this time. So I've got 600 minus 2w equals 2 times the length, and that means that our length equals 300. Oh, it's not 2 times rw, it's 3 times rw. So that means our length is 300 minus 3/2 times our width. Perfect. So that's what length is. Now let's substitute it into our area equation here. So our area can be represented as 300 minus 3/2 times our width times the width. So an equation that represents the area of this enclosure can be, I'm going to multiply this in, and I'm going to write it in standard form. So I'm going to start with this piece. Negative 3/2 w squared plus 300 w. Now we could graph that, and this negative shows us that the graph of it is going to look like this. And we want to optimize it. So when we graph it, it looks like this, and it's looking at the relationship of our area to our width. So I want to know right here, to get the maximum area, what does my width need to be? Well, my width, remember, that's going to be our axis of symmetry, or our x value. So how could I find that axis of symmetry? Well, I'm going to do our width equals negative b over 2a, just like we've been doing. So negative 300 over 2 times negative 3/2. Well, that's going to be negative 300 over negative 3, which equals 100. So if my width is 100, that'll optimize my space there. So we want the width to equal 100 feet. Now, if our width equals 100 feet, what does that mean that our length equals? So our length is going to be 300 minus 3/2 times 100. Now, what this really is our length equals 300 minus, well, 300 over 2, which is 150. So that means that our length equals 150. So if our width is 100, our length is 150. So that would be the dimensions of our rectangle. And the length of all of the sides should be 100, 100, 100, 150, 150. And if we add that up, 150 plus 150 is 300, 400, 500, 600. Perfect. That's our optimized area there. So that is how we would do it if we want to construct that. Every time we're going to start by writing that equation that represents the perimeter. Then we're going to find the area and optimize it based on that quadratic that the area creates. So let's try this one more time all together. In this case, it's a little bit different. So you have 90 feet of fence, which is not very much, but we want to construct an enclosure again for our pet goats, because who doesn't love goats? We want to have 2 enclosures again, just like we did last time, but they share a side with our barn. The thing that makes this awesome is that this side with our barn, we don't have to calculate in. So as we're looking at that 90 feet, our 90 feet is going to be the length over here, plus the width, plus the width, plus the width. But it doesn't have to include this other side because the barn creates that other side to block it off. So our 90 feet is going to be our length plus 3 times our width. Fantastic. And then we need to use that to calculate our area, so the length times the width. Now remember, what we do every time here is we are going to use this equation to solve for one of the variables, and then we're going to substitute that variable into our area equation and use that to make our area into a quadratic. Once we have that area as a quadratic, we can graph it, or we can remember that what it's going to look like is it's going to look like a quadratic equation, either opens up or opens down, and we want to find that maximum to figure out what is the length's going to be so that we have the most area for our goats to roam. So as we're doing this problem here, let's solve for something. I'm going to solve for L because it doesn't have a coefficient or a number in front. So minus 3W minus 3W, L equals 90 minus 3W. Fantastic. So that's what L equals. And now what I want you to do is I want you to finish out this problem. So if our length represents 90 minus 3W, let's substitute it right in here for our length and get what does the area equal? What is that equation that we're going to have here, that quadratic equation? Once we have our quadratic equation, use it to maximize to figure out our width, and then use that width to calculate our length. Once you've finished calculating that, go ahead and unpause the video and check for the solution, and we'll go over how we find that solution all together. Okay, hopefully you've had a chance to go over this problem. So we stopped there by substituting the length in to our area equation. So as we substitute that in, we end up getting this quadratic to represent it. A equals negative 3W squared plus 90W. Now what that looks like is it's going to be something like that one on the left. It's going to open down, and the relationship we're comparing is the area to the width. So what we need to figure out to determine what that max area is what width will give us that max area, and that width that we need is going to be the axis of symmetry. So our width equals negative b over 2 times a, or negative 90 over 2 times negative 3. As we simplify that, we get 15. So that means our width has to be 15 to get that maximum area. So if our width is 15, what does that mean our length is? Well, we can substitute that 15 back into this length equation that we calculated here. And as we substitute in, we get that our length equals 45 feet. So when we're doing these optimization problems, or these problems where we're trying to use our fencing and get the most area, what we want to do is we want to set up that perimeter, or that equation that represents the fencing itself. So what are my lengths and widths? How does that relate to our fencing? How many widths do I have? How many lengths do I have? And then use our area equation based on the substitution of those values that we get from that original one to find a quadratic. Now, area is always units squared, which is why it turns into a quadratic. And this is how we can get that quadratic shape and find the maximum in order to optimize the amount of area. And that's how we do that when we're trying to figure out how much area can we get for that resource. Please check out the next video in which we'll discuss how we can use quadratics to optimize how much money we make. So how can I make the most money by charging someone a certain amount and getting the right number of people? So go ahead and check out the next video to see what we do there.